Now we're going to look at determining empirical formulas using percentage composition. Your empirical formula, remember, is the lowest whole number ratio between elements in a compound. And you can determine this from your percentage composition. So if you're given a percent composition of each element in a compound, let's say, for example, you have 30% of a compound is carbon, and you had a 100-gram sample, then you could assume that 30 grams of that compound would also be carbon. So basically all you have to do on these is take whatever your percentage is for each element, express it in grams, and then you're good to start on this particular process. So the next slide just has a lot of information. We're going to skip that for now. You can go and read it. But we're going to go ahead and start and do this first example. So if I have 75% that is carbon, we're going to say that that's the same as saying 75 grams out of a 100-gram sample is carbon. 25 grams for the 25% of hydrogen. Now remember, when you're writing the formulas, the subscripts represent mole values. So what I need to do first is take my grams to moles. So then that's what I'll do. I'll convert each of these gram values to moles. I know that in 1 mole of carbon, there's 12 grams of carbon based on the atomic mass. For hydrogen, for 1 mole of hydrogen, there's 1 gram of hydrogen. So if I divide these out, 75 divided by the 12 is going to give us 6.25 moles of carbon. Dividing this one out, of course, would be 25 moles of hydrogen. Now, since we want the lowest whole number ratio, then what you want to do on these is take the lowest one of these mole values, so in this case it would be the 6.25 mole values, and divide both of these by 6.25. That's going to ensure us that one of these is 1, which should be this top one. And then if we divide our 25 by the 6.25, that's going to give us, in this case, 4. Since we have whole numbers, then we can write our empirical formula assuming that 1 mole of carbon to our 4 moles of hydrogen. That would be our empirical formula. So to review the steps, you'll take your percentages, express them in moles, take your percentages, express them in grams, convert your grams to moles. Once you get your mole values, you'll divide all the mole values by the lowest mole value, in this case 6.25. That will give your lower whole number values. Now, should you get something where you get to this point and you get like a 0.5, something like that, you can't really round that up. So what you need to do anytime you get a 0.5 as your second value here, after you've divided by the smallest now, you're going to multiply all the mole values by 2 to ensure that you get a whole number. If you got a 0.33 type situation, you'd multiply all by 3. Those are really going to be the only cases where you'd have to do an extra step on this particular type of problem. So let's look at number 3. This one has 3 elements working in exactly the same way. So we've got 22.1% aluminum, so we're going to express that as 22.1 grams of aluminum. We have 25.4% phosphorus, so that would be our 25.4 grams of phosphorus. And then oxygen, 52.5 grams of oxygen in lieu of the 52.5%. Once we get it in grams, we change it to moles. So we'll take each of these, divided by their atomic mass. So we know aluminum is 27. We know phosphorus is 31. And remember, I'm getting these off of your periodic table. Oxygen is 16. So each of these I'm doing so that I can get rid of the gram units and get to moles. So my 22.1 divided by my 27 is going to be 0.8185 moles of aluminum. My 25.4 phosphorus divided by 31 is 0.8194 moles of phosphorus. And the 52.5 divided by the 16 is going to give me my 3.28 moles of oxygen. This is our smallest one, so we'll divide all of them by the 0.8185. This one's going to be 1 mole of aluminum. If you divide this one out, 0.8194 divided by 0.18185, you're going to get 1.00, so that's approximately 1 as well. 3.28 divided by 0.8185 is going to give us 4. So again, since we get all whole numbers, then my formula, empirical formula, would be Al, one of those, 1 phosphorus, and then 4 oxygens. So there's some others to try. So the last thing we'll look at real quickly is determining empirical formulas. Determining molecular formulas from empirical formulas. Your molecular formula is what's referred to as the true formula, so it can be a multiple of your empirical formula. So I'm going to use empirical formulas to be EF, EM for the empirical mass, MM for the molecular mass. Basically what you'll be doing on this one that makes it a little different from the others is you can actually have the empirical formula and then you'll be given a molecular mass and you'll compare that to the empirical mass to determine how much bigger that particular formula is. So let's look at this first one. We have an empirical formula of NO2, so that's our lowest whole number ratio. Its molecular mass is 92 grams per mole, and we want to find out what its molecular formula is. So what I need to do is take my empirical formula, which is my NO2, and find its mass. So I have 1 nitrogen at 14, 2 oxygens at 16, for a total, do that right? That should be 32, sorry. Be 46. So now I'm going to take my molecular mass, in this case which would be the 92 grams per mole, and I want to divide it by the empirical mass, which we just solved for, which was 46 grams per mole, and I should get a whole number. In this case, I get 2. What that 2 is telling me is that my molecular formula is twice as big as my empirical formula. So now all I have to do is take my empirical formula, which is NO2, and multiply each subscript by that 2. So I would get N2O4, and that would be my molecular formula. If I want to check and make sure that this is correct, all I have to do is I'll take my 2 nitrogens, multiply them by 14, my 4 oxygens, multiply them by 16, add that together, and well, if I can do this right. That should be 64, sorry. So I'm going to get 92, and this matches up with what I got here earlier. Now we don't always start with having that particular empirical formula. So here's another one you can try for the empirical formula. So let's look at one where you don't have the empirical formula. So basically all you have to do is combine the last 2 things we did all into one problem. So we have 40%, that's carbon, so we're going to express that as 40 grams of carbon. We have 6.7% hydrogen. We'll express that as 6.7 grams of hydrogen. We have 53.5% oxygen. We'll express that as grams of oxygen. So the first thing we got to do is get our empirical formula. So now we'll take each of these grams, convert them into moles. So I know 1 mole of carbon is equal to 12 grams of carbon based on the atomic mass. 1 mole of hydrogen, 1 gram of hydrogen based on its atomic mass. 1 mole of oxygen, 16 grams of oxygen based on its atomic mass. So now we put everything in the calculator. So 40 divided by 12 is going to give me 3.33 moles of carbon, 6.7 moles of hydrogen, 53.5 divided by 16, 3.34 moles of oxygen. We'll divide everything by 3.33. So I'm dividing by my lowest ratio, so this will be a 1 mole here for my carbon. If I divide that, that would be 2 moles here for my hydrogen. This will be 1 mole here for my oxygen. So my empirical formula will be CH2O. So now that I have the empirical formula, the next thing I want to do is find the mass of the empirical formula. So I have 1 carbon times 12, 2 hydrogens times 1 oxygen times 16, which would be 30, if I did that right. So that will be the empirical mass of my empirical formula. Once I get the empirical mass of my empirical formula, then I want to compare that to the molecular mass, which they need to tell me this in the problem. So it says its molecular mass is 60 grams per mole. So I'll take my molecular mass, divide it by my empirical mass that we just solved for. That's going to give us 2. Remember, this is going to be what I need to use to multiply each of my subscripts up here by that 2. So my molecular mass then would be C2H4O2. That would be my molecular formula. So there's others for you to try and see how you do on those.